Learning about equations of motion by graphical method. Graphical representation of motion. Graphs provide a convenient method to present basic information about a variety of events. For example, in the telecast of a one-day cricket match, vertical bar graphs show the run rate of a team in each over. As you have studied in mathematics, a straight line graph helps in solving a linear equation having two variables. Distance, time graphs. The change in the position of an object with time can be represented on the distance-time graph adopting a convenient scale of choice. In this graph, time is taken along the x-axis and distance is taken along the y-axis. Distance-time graphs can be employed under various conditions where objects move with uniform speed, non-uniform speed, remain at rest, etc. We know that when an object travels equal distances in equal intervals of time, it moves with uniform speed. This shows that the distance traveled by the object is directly proportional to time taken. Thus, for uniform speed, a graph of distance traveled against time is a straight line. Equations of motion by graphical method. When an object moves along a straight line with uniform acceleration, it is possible to relate its velocity, acceleration during the motion, and the distance covered by it in a certain time interval by a set of equations known as the equations of motion. There are three such equations. These are V is equal to U plus AT, S is equal to UT plus half AT square, 2AS is equal to V square minus U square. Let us draw AD parallel to OC. From the graph, we observe that BC is equal to BD plus DC, that is equal to BD plus OA. Substituting BC is equal to V and OA is equal to U, we get V is equal to BD plus U, or BD is equal to V minus U. From the velocity time graph, the acceleration of the object is given by A is equal to change in velocity divided by time taken, that is equal to BD divided by AD, that is equal to BD divided by OC. Substituting OC is equal to T, we get A is equal to BD divided by T, or BD is equal to AT. Equation for position-time relation. Let us consider that the object has traveled a distance s in time t under uniform acceleration a. The distance traveled by the object is obtained by the area enclosed within OABC. under the velocity time graph AB. Thus, the distance s traveled by the object is given by S is equal to area OABC, which is the trapezium, that is equal to area of the rectangle OADC plus area of the triangle ABD, that is equal to OA multiplied by OC plus 1 by 2 AD multiplied by BD. Substituting OA is equal to U, OC is equal to AD is equal to T, and BD is equal to AT, we get S is equal to U multiplied by T plus 1 by 2 T multiplied by AT, or S is equal to UT plus 1 by 2 AT square. Equation for position-velocity relation. From the velocity time graph, the distance s traveled by the object in time t, moving under uniform acceleration a, is given by the area enclosed within the trapezium OABC under the graph. That is, S is equal to area of the trapezium OABC, that is equal to OA plus BC multiplied by OC divided by 2. Substituting OA is equal to U, BC is equal to V, and OC is equal to T, we get S is equal to U plus V multiplied by T divided by 2.
From the velocity-time relation, we get T is equal to V minus U upon A.
Using equations, we have S is equal to V plus U multiplied by V minus U divided by 2A, or 2AS is equal to V square minus U square. Example: a train starting from rest attains a velocity of 72 km per hour in 5 minutes. Assuming that the acceleration is uniform, find the acceleration and the distance traveled by the train for attaining this velocity. Solution: we have been given U is equal to 0, V is equal to 72 km per hour, that is equal to 20 meter per second, and T is equal to 5 minutes, that is equal to 300 seconds. 1. From equation, we know that A is equal to V minus U divided by T, that is equal to 20 meter per second minus 0 meter per second divided by 300 seconds, that is equal to 1 divided by 15 ms raised to the power minus 2. 2. From equation, we have 2AS is equal to V square minus U square, that is equal to V square minus 0. Thus, S is equal to v square divided by twice a. That is equal to 20 meter per second, the whole square, divided by 2 into 1 divided by 15, ms raised to the power minus 2. That is equal to 3000 meter. That is equal to 3 kilometer. The acceleration of the train is 1 by 15 ms raised to the power minus 2, and the distance traveled is 3 kilometer. Example: a car accelerates uniformly from 18 km per hour to 36 km per hour in 5 seconds. Calculate the acceleration and the distance covered by the car in that time. Solution: we are given that u is equal to 18 km per hour, that is equal to 5 meter per second. V is equal to 36 km per hour, that is equal to 10 meter per second. And t is equal to 5 seconds.
From equation, we have A is equal to V minus U upon T. That is 10 meter per second minus 5 meter per second upon 5 second is equal to 1 meter per second square.
From equation, we have S is equal to ut plus 1 by 2 at square, that is equal to
5 meter per second into 5 second plus 1 by 2 into 1 meter per second square into 5 second whole square.
That is equal to 25 meter plus 12.5 meter, that is equal to 37.5 meter. The acceleration of the car is 1 ms raised to the power minus 2, and the distance covered is 37.5 meter. That is all in this topic, students. Let us learn about uniform circular motion. Learning is fun.